Swayam Prabha. Digital India. Educated India.
Now you are supposed to find what this radial function u of r is. For that we have to run through the procedure of finding the strain, finding the stresses, finding using the equilibrium equations to find the unknown displacement component. Okay. So now the gradient of displacement h is given by, from that expression in here, dou u r by dou r, that is the only component of stress which is non-zero. Here you add this is a non-zero component, u r as a function of theta is not there, this is 0, u theta is 0, so this is 0 and this is also 0 because it is not a function of z. Okay. So you have dou u r by dou r 0 0, u theta is not there, so all this remaining components except u r by r are 0 because there is no u theta and there is no u z in this problem. Okay. So you have 0 u of r by r 0 0 0 0. Okay. The strain corresponding to this displacement gradient would be 1 of h plus h transpose, which will be same as h in this case, which will be du r by dr 0 0 0 u r by r 0 0 0. Okay. Now we will use a constellation for sigma, which is sigma times, sigma is Lamé constant lambda times trace of epsilon identity plus 2 mu epsilon. Okay. This will give me the non-zero components are the diagonal components of the stress, which is a radial stress sigma r r. This will be nothing but sigma r r, sigma r theta, sigma r z, sigma r theta, sigma theta theta, sigma theta z, sigma r z, sigma theta z, sigma z z are the cylindrical polar components of the stress, and the strain components are cylindrical polar components of the strain. So I am equating the sigma r r with this equation. So it will be lambda plus 2 mu du r by dr plus lambda times u r by r. Okay. Similarly, sigma theta theta would be lambda plus 2 mu u r by r plus lambda times du r by dr, and sigma z z would be lambda times du r by dr plus u of r by r. Okay. Okay. Now I substitute these expressions into divergence of sigma equal to 0. Okay. Now divergence of sigma is given by this expression in there. Okay. So it is given by the expression in here. Okay. Divergence of sigma is given by the expression in here. Here you find that sigma r theta component is 0, so this goes to 0, r z is 0, whereas sigma r r and sigma theta theta are not 0. So you have, for in the first equation you will retain d sigma r r by dr plus sigma r r minus sigma theta theta by r, that will be retained. In the second equation you find that sigma r theta is 0, sigma theta theta is not a function of theta, hence this is 0, sigma theta z is 0 and hence this is 0, this is also 0 and sigma r theta is 0. So this equation trivially boils down to 0. In a similar manner, the last equation sigma r z and theta z are 0 and sigma z z is not a function of z, and hence this equation also boils down trivially to 0. Okay. We are assuming that there are no body forces acting in the cylinder and the cylinder is in static equilibrium, and hence the values of sigma has to be equal to 0. Okay. Assuming no body forces and static equilibrium. Okay. Now, what we will do next is we will substitute for sigma RR, sigma theta theta in this expression in here. Next we will substitute sigma RR and sigma theta theta into the expression here, and we will see what is the differential equation we are getting. If I substitute sigma RR and sigma theta theta there, I will get lambda plus 2 mu d square ur by dr square plus lambda d by dr for by r plus 2 mu by r dur by dr minus ur by r equal to 0. Okay. Now, I can rewrite this equation as lambda plus 2 mu ur by dr square plus d by dr u of r by r equal to 0, since I observe that 1 by r dur by dr minus u of r by r is nothing but d by dr u of r by r. Okay. Since that is that, I get this as this. Okay. Now, I know from our restriction on material parameters that lambda plus 2 mu is not equal to 0. So, I require d square ur by dr square plus d by dr u of r by r to be equal to 0. Now, so integrating this once I get dur by dr plus u of r by r equal to C1. Okay. Now, again I realize that I can rewrite this as d by dr u of r 1 by r equal to C1. Okay. So, this will imply integrating this, I will get r u r is C1 r square by 2 plus C2. Okay. From here I get u of r to be C1 r by 2 plus C2 by r. Okay. Where I have to find the constant C1 and C2 from the boundary conditions. Okay. For the problem that we are studying, let us see what the boundary conditions are. Okay. For this problem, let us see what the boundary conditions are. The boundary conditions are, I am applying a pressure at the inner surface. This pressure is acting, this is the outward normal to that surface, it is acting opposite to the outward normal to the surface. So, that is a negative stress. Okay. And this component of stress, this normal is nothing but ER, negative of ER, okay, where ER is the radial basis for this cylindrical polar coordinate system. So, this stress is sigma RR stress, okay, or I can more formally derive the boundary condition as T of ER, the negative phase, is given by plus PI ER, right, because it is acting along the EI direction. Okay. Now, T of minus ER is sigma RR 0 0 0, sigma theta theta 0 0 0, sigma ZZ. This was the state of stress that we got for this problem into minus 1 0 0. So, this will give me minus sigma r r 0 0, okay, at the inner surface evaluated at the inner surface, that is r I. Okay. So, what I get is I get minus sigma r r at r I is equal to P I, or sigma r r at r I is minus P I. Okay. Now, similarly at the outer surface I am applying no traction. So, T's of E r, the outer surface the normal is this, normal is that, okay, that is a positive E r dash normal. So, T's of E r is 0 vector. So, this will imply that sigma r r at r naught is equal to 0. Okay. I can alternatively I could have applied a pressure at the outer surface, in which case whatever pressure that I apply at the outer surface should come in here as a pressure that I am applying there. Okay. But for example problem here I am assuming it to be 0. Okay. So, these are the two boundary conditions that I have to now enforce. Okay. I found the displacement field to be, I found u of r to be C1 r by 2 plus C2 by r. Okay. Correspondingly, now I go back and substitute this in the expression for the stresses in here, the expression for the stresses in here, okay, and I will evaluate what the stresses are in terms of the constant C1 and C2 and radial location r. Okay. So, sigma r r now becomes lambda plus 2 mu C1 by 2 minus C2 by r square plus 2 mu plus lambda C1 by 2 plus C2 by r square, which can be written as lambda plus mu C1 minus 2 mu C2 by r square. Okay. Similarly, the expression for sigma theta theta becomes lambda plus 2 mu C1 by 2 plus C2 by r square plus lambda times C1 by 2 minus C2 by r square, which can be written as lambda plus mu C1 plus 2 mu C2 by r square. Okay. And sigma ZZ now will be lambda times C1 by 2 plus C2 by r square plus C1 by 2 minus C2 by r square, which will be lambda times C1. Okay. Now, I apply the boundary conditions, sigma r r at r I equal to minus p and sigma r r at r naught equal to 0 to obtain the following equations. Applying the boundary conditions, you get lambda plus mu minus 2 mu by r I square, lambda plus mu minus 2 mu by r naught square to C1 C2 is equal to minus Pi 0. Okay. Now, I solve this equation to get from here C1 C2 is 1 by lambda plus mu 2 mu 1 by r I square minus 1 by r naught square, okay, into minus 2 mu by r naught square minus 2 mu by r I square minus lambda plus mu and lambda plus mu into minus Pi 0. Okay. That gives us the constant C1 to be pi r I square divided by lambda plus mu into r naught square minus r I square, and C 2 would be 1 by 2 mu r naught square minus r I square pi r naught square r I square. Okay. Now, correspondingly, having found the constants, I can write the stresses. Sigma r r would be pi r I square divided by r naught square minus r I square into 1 minus r naught by r whole square. Okay. And sigma theta theta would be pi r I square by r naught square minus r I square into 1 plus r naught by r the whole square. Okay. Similarly, sigma z z would be lambda by lambda plus mu into pi r I square by r naught square minus r I square. From the definition of Poisson's ratio, you know that this is nothing but Poisson's ratio times pi r I square divided by r naught square minus r I square. Okay. Okay. Now, let us plot the variation of sigma r r and sigma theta theta and sigma z z along the thickness of the cylinder. Okay. Okay. Now, first let us plot the variation of sigma r r across the thickness of this cylinder. Okay. You know that at the inner surface when r equal to r I, sigma r r is minus pi. So, this is minus pi, and at the outer surface when r equal to, when small r equal to r naught, this becomes 0. So, it varies from pi minus pi to 0 like this. It is 1 by r square. So, it will be an hyperbolic kind of a variation there. Okay. This is sigma r r variation. On the other hand, sigma theta theta, now let us plot sigma theta theta variation. Sigma theta theta at r I would be pi r naught square plus r I square divided by r naught square minus r I square. Okay. And sigma theta theta at r naught would be 2 times pi r I square divided by r naught square minus r I square. You can see that it decreases from the value at the inner surface to the outer surface, but it is not 0 and it is positive throughout the domain. Okay. So, sigma theta theta will vary like that, and this is sigma theta theta at r I and this is sigma theta theta at r naught. Okay. Okay. Now, the point is the hoop stress or sigma theta theta stress is tensile in nature. Okay. And the actual stress is constant over the entire cross section, it does not vary radially, that is what we got from our derivation. Now, let us understand why there is axial stress and radial stress developed in the cross section. Okay. Now, because hoop stress is tensile, due to Poisson's effect there will be a lateral contraction along the thickness direction and the axial direction, but in the axial direction what we have done is we have fixed the length to be a constant. Okay. Since the length has been fixed to be a constant, there should be axial tension coming in to maintain the constant length, and hence you have sigma zz, which is a tensile stress, which is a constant stress across the cross section. Okay. Similarly, you will find that epsilon r r, which is dou u r by dou r, is not 0. Okay. Dou u r by dou r is C1 by 2 minus C2 by r square, which has some value which is non 0. Okay. And hence what happens is there will be a thickness change in the cross section. Okay. Okay. So, what we have seen in this lecture is we have seen how to analyze pressure vessels, thick wall pressure vessels to be more specific. We saw what a displacement field is, and we saw how to get the stresses, and we saw how to get the stresses in a thick wall cylinder. Okay. We will stop here for today. Thank you.